Hello. Today we are going to see hydraulic turbines. So, what is meant by hydraulic turbine? So, it is a machine which converts either hydraulic energy possessed by water into mechanical energy, which is further converted into electrical energy or mechanical energy into hydraulic energy. Machine converts hydraulic energy into mechanical energy are called hydraulic turbines. So, those machines which converts mechanical energy into hydraulic energy are called as pumps. Today we are going to see about turbines. Turbines are defined as the hydraulic machines which converts hydraulic energy into mechanical energy. This mechanical energy is used in running an electrical generator, which is directly coupled to the shaft of the turbine. Thus, the mechanical energy is converted into electrical energy. The electrical power, which is obtained from the hydraulic energy, that is, from the water, is known as hydroelectric power. At present, the generation of hydraulic power is the cheapest as compared by the power generated by other sources such as oil, coal, etc. So here you can see in the diagram. So there is a so let us consider water is stored in a dam, right? So the top surface level of the water we calling it as a head raise. So the from the bottom, right? So ground level to the top surface level we calling it as a total. We calling it as a gross head. Okay. So the water is coming out from the dam. We are connected through a penstock, right? So it is a uh, channel which is used to move the water. So the large diameter pipe, circular pipe, which in which the water flows, and it flows to the nozzle. Okay, nozzle where there is an increase in kinetic energy by drop of pressure energy. So this nozzle increases the kinetic energy of water, right? So this water, which is coming with a high velocity, strike the buckets of the Pelton wheel. So this turbine, right? We call it as a Pelton wheel turbine. So it causes the Pelton wheel to rotate. So the net head is the difference between the gross head and the head loss, right? While moving from dam storage to the tail race, right? So some of the water will be lost in this tail race also. Okay, now we are going to see layout of hydroelectric power plant. Okay, so the dam is constructed river to store the water. Pipes of large diameter, we calling it as a penstock, which carry water under pressure from storage reservoir to the turbines. It has a turbine has different types of vanes fitted to the wheels. A tail race, which is channel which carries away the water from the turbine. Right. So some of the definitions and of heads and efficiency of a turbine are a gross head. So it is nothing but the difference between the head race level and the tail race level when no water is flowing across a gross head. It is denoted by Hg. So net head is called as, it is also called as effective head, and it is defined as a head available at the inlet of the turbine. When water is flowing from head race to the turbine, a loss of head due to friction between the water and penstock occurs. Right? So we already know about that friction loss. When the water flows through a pipe, where we have derived a formula for the friction loss when water is flowing through a pipe. That is called as Darcy-Weisbach equation. HF equal to 4FL V square by D into 2G, right? So the efficiency of the turbine. So some of the important efficiency we are going to consider while calculating the performance of the turbine are hydraulic efficiency, mechanical efficiency, volumetric efficiency, and overall efficiency. This hydraulic efficiency is nothing but a ratio of power delivered to the runner power to the power supplied at the inlet. Or in very simple terms, it is the ratio of runner power to the water power, right? So the runner power delivered for Pelton turbine is W by G into VW1 plus or minus VW2 into U divided by 1000. So in case of radial flow turbine, this runner power varies by VW1 into U1 plus or minus VW2 into U2 divided by 1000. Whereas water power is power supplied to the inlet of the turbine. So this is nothing but a W into H divided by 1000. So H is the head and W is the weight of water striking in the turbines per second. Okay, so the water power in terms of kilowatt, if you're writing means we are writing to rho GQH by 1000. So we already know the density of water is 1000. So when we cancel 1000 on numerator and denominator, we will get GQH, right? So the next one is mechanical efficiency. The mechanical efficiency is nothing but a ratio of power at the shaft of the turbine to the power delivered by water to the runner. Or in simple terms, it is the ratio of shaft power to the runner power. So next one is volumetric efficiency. So volumetric efficiency is the ratio of volume of water actually striking the runner to the volume of water supplied to the turbine. Okay, coming to the overall efficiency, it is defined as the ratio of power available at the shaft of the turbine to the power supplied by water. Or in simple terms, it is shaft power to the water power. By other means also, we'll be getting overall efficiency is by multiplying mechanical efficiency and hydraulic efficiency, we will get the overall efficiency. Okay, so here some of the classification of hydraulic turbines. So there are many kinds of hydraulic turbines available. So some of the important classification based on according to the type of energy, according to the direction of flow, according to the head at inlet of turbine, specific head of the turbine. Here are some of the turbines we are going to discuss. So first one, according to type of energy at inlet, we can classify it as impulse turbine and reaction turbine. So in very simple meanings or simple terms, impulse turbines are those which possess both kinetic energy and pressure energy at the inlet of the turbine. Reaction turbines possess only kinetic energy. So according to the direction of flow through runner, we can classify it as tangential flow turbine, radial flow turbine, axial flow turbine, mixed flow turbine. So the way which the water strike the vanes of the turbine. So according to which we are classifying to the direction of flow. So according to the head, so head available at the inlet of the turbine, whereas whether it is a high head turbine, low head turbine, or medium head turbine. So according to specific speed of the turbine, we are classifying it as a low specific speed turbine, medium specific speed turbine, high specific speed turbine. So as I already told you, in the inlet of the turbine, the energy available is only kinetic energy, then the turbine is known as impulse turbine. If the water possesses both kinetic energy as well as pressure energy, the turbine is known as reaction turbine. So the important components or arrangements of Pelton wheel turbine are nozzle and flow regulating arrangement sphere, runner and buckets, caging and braking gauge. These are the main components of Pelton wheel turbine. So here in this diagram, you can see this Pelton wheel turbine. So it is a wheel-shaped, cup-shaped design which is built over the circumference of the wheel. The flow will be striking at a tangential. So it is called as tangential flow impulse turbine. It possesses only kinetic energy while striking at the vanes. So it is a tangential flow impulse turbine. Pelton wheel turbine is also called as tangential flow impulse turbine. So when the water strikes with a velocity, absolute velocity, then bucket wheel of the Pelton turbine will rotate. So here you can see this water will be striking directly at the splitter present in the Pelton wheel turbine. So the jet of water striking. So this can be adjusted with the help of spear arrangement. So the runner will rotate the Pelton wheel, which in turn it is attached to the shaft, which produces electricity, electrical generator, which produces electricity. So we can obtain energy in this way. So here you can see this is a large type of turbine built for production of energy. So now we are going to see velocity triangles and work done for Pelton wheel. As you are aware that velocity triangles of a turbine consist of absolute velocity, flow velocity, whirl velocity, relative velocity at inlet as well as at outlet. The absolute velocity is nothing but the velocity with which the jet of water striking the vane. So we're calling it as an absolute velocity. If the absolute velocity is striking the jet of water within certain angle, then that force, that velocity will be resolved into horizontal component and vertical component. The vertical component, we're calling it as a flow velocity, whereas the horizontal component, we're calling it as a whirl velocity, which makes an angle alpha. So at the same time, the velocity of water striking the vane, and the vane will rotate with the blade velocity that is called as u or tangential velocity. So the difference between this tangential velocity and the absolute velocity, we calling it as a relative velocity. So it is present for both inlet triangle and outlet velocity triangle. So here you can see the absolute velocity of water, right, which is coming out from the nozzle, striking the Pelton wheel bucket, exactly striking on the splitter. So here it is not making an angle. So the alpha value becomes zero, which in turn there is no flow velocity. So the vertical component becomes alpha value becomes zero. So the vertical component becomes zero. So we are having only horizontal component, which is equal to whirl velocity. So the absolute velocity of the water which is striking the proton wheel, which is equal to the whirl velocity of the component, right? So the which the speed at which the Pelton wheel moves, whereas the velocity which the water strikes. So the difference between that V1 and U1, right? Absolute velocity and the tangential velocity or blade velocity which is the Pelton wheel moves. This difference we calling it as a relative velocity. So you can see this inlet triangle. So this is the absolute velocity. This is the blade velocity. The absolute velocity is equal to whirl velocity. So the difference between the absolute velocity and the tangential velocity or blade velocity, which will gives the relative velocity. So this is the inlet velocity triangle for Pelton wheel turbine. Whereas when you consider outlet velocity triangle, so here you can see the angle of deflection. The angle of deflection is phi, denoted by phi. So the angle with which the blade gets deflected when the water striking the Pelton wheel. So it is phi. It is making an angle of phi. So the relative velocity is VR2. So the absolute velocity, which is the water striking the blade, and it comes out with the velocity of V2. So we are, as already said, we are having two components for absolute velocity. One is horizontal component, calling it as a whirl velocity, and vertical component, we're calling it as a flow velocity. So which is making an angle beta. So VW2 is the whirl velocity at outlet. VF2 is the flow velocity at the outlet. Okay, the relative velocity which is making an angle phi. So there is an blade velocity at outlet U2. So this is the simple form of velocity triangle for Pelton wheel turbine. So the some of the important definitions we already know, right? So net head acting on the Pelton wheel is gross head minus head loss. And then head loss, the gross head loss is we already know as per Darcy-Weisbach equation 4FL v square by 2GD. Velocity of jet at inlet, absolute velocity is given by the formula square root of 2gh. The tangential velocity or blade velocity is calculated by using the formula pi dn by 60. So this is the diameter of the runner. N is the with which RPM it rotates, divided by 60 will give you the tangential velocity. So the velocity triangle at inlet will be a straight line since we are getting VW1 equal to V1, alpha equal to 0 and theta equal to 0. Right. Next, from velocity triangle at outlet, we are getting the equation VR2 equal to VR1 and VW2 equal to VR2 cos phi minus U2. The force exerted by jet of water in the direction of motion is given by the equation Fx equal to rho into A into V1. So sum of whirl velocities VW1 and VW2. So from the above equation, you can get the weight of water striking the per second, kinetic energy of jet per second of mv square. Very simple. We already know the formula of mv square. The mass is given as rho a v1 into v1 square is the absolute velocity. Hydraulic efficiency, you can derive work done per second to the kinetic energy of jet per second. Work done per second is here you have derived the formula rho a v1 vw1 plus vw2 into u divided by half mv square. So by solving this equation, you will get 2 into sum of whirl velocities into tangential velocity by absolute velocity. So hydraulic efficiency, you will also get this equation also for deriving the problem, for solving the problem. So maximum hydraulic efficiency you will get in the terms of 1 plus cos phi by 2. So where you can get it will be maximum when the velocity of wind is of the velocity of jet of water at inlet. So We'll get the maximum hydraulic efficiency when the Pelton will be maximum is when the velocity of wheel is half the velocity of jet of water at inlet. If this condition happens, the hydraulic efficiency will be maximum. So this maximum efficiency can be found out by using the formula 1 plus cos pi by 2. So these are some of the points important to be remembered for the Pelton wheel. So the absolute velocity is given as CV. CV is nothing but coefficient of velocity, which is 0.98 or 0.99, whatever may be given in the problem, into square root of 2gh. The velocity of wheel U is given by U equal to pi into square root of 2gh. Yes, I have already told you, U can be found out by using the formula pi dn by 60. Also by the formula using speed ratio, right? The mean diameter, pitch diameter, D can be found out using this formula. Jet ratio can be found out by using the formula D by D. Number of buckets on a runner is given by formula Z equal to 15 plus D by 2D. So using these important points, you can design a Pelton wheel of required element. Thank you.